Question: if every weather satellite went blind during a hurricane at night, who would still see what's happening on the ground? Optical cameras can't see through clouds or darkness, but that's exactly when the most critical decisions need data. So how do space agencies monitor floods, oil spills, and collapsing infrastructure when the sky shuts down? Stay with me, because in the next minutes you'll find out how radar satellites light up Earth with their own microwaves, read the echoes, and build sharp images from storms and shadows. This isn't sci-fi, it's synthetic aperture radar, and it changes what's visible. What if the most advanced eyes in space fail exactly when a storm is strongest? How do you act with no eyes on the ground? That's not a hypothetical. Optical satellites depend on sunlight and a clear path to the surface. They don't see objects directly, they measure reflected light. No light means no reflection. Clouds scatter and absorb that light before it ever reaches the ground. So the sensor gets a bright, textured ceiling and not the flooded neighborhood underneath. You can widen spectral bands, tweak exposure, or fly more cameras, but all you're collecting is illumination that never made it through. Night plus cloud cover turns that limit into a double blackout. During hurricanes and typhoons, convective towers stack up like walls, and the storm canopy spreads for hundreds of kilometers. Wildfire smoke behaves like a moving overcast, thick enough to block visible and mini-infrared bands when firefighters need to see fire edges and new ignitions. The data feed slows to a crawl at the exact moment timing matters most. You can task the best optical constellations for repeat passes, but until the veil thins or the sun returns, you're staring at cloud texture and smoke gradients and calling it a day. Take a landfalling hurricane at 2 in the morning. Surge is pushing into back bays, levees are under stress, and low bridges may be washed out. Emergency managers want updated flood extents, passable road segments, and staging areas that aren't turning into islands. High-resolution optical satellites respond, but the frames only show cotton-like cloud tops and overshooting tops near the eye wall. The ground network gets dark maps with almost no ground truth, so crews roll out with incomplete information and precious hours slip away. This isn't rare bad luck. At any given moment, roughly 6 out of 10 places on Earth sit under cloud. In the tropics and during monsoon seasons, decks hang around day after day, often building by noon and lingering into the night. Even the near-infrared bands popular for vegetation maps can't punch through thick convective tops or layered stratus. Thin cirrus might leak some light. Deep cloud shields keep secrets. Now switch scenes to an offshore oil platform in rough weather. A pipeline leaks under a storm deck. The slick spreads, thinning into hairline sheens at the edges. Visible sensors can't see through the cloud, and thermal contrast between oil and water at night is small. Decision makers are left waiting for a gap, while wind and currents redistribute the slick and push it toward a shipping lane. Time matters, but the sky isn't cooperating. In bad weather, surveillance gaps also create blind spots for moving targets. Under an overcast, optical systems lose shadow cues and color signatures that help separate vehicles from background clutter. Camouflage works better when everything is washed into the same diffuse gray. Small boats, low-profile vehicles, or decoys sit right under the cloud and slip the net because the net is made of reflected sunlight. The environment pays too. Regions with constant cloud belts see logging fronts advance without timely detection. Clear day images arrive after roads and skid trails are already cut. At high latitudes, winter darkness hides glacier calving and ice shelf rifts forming in real time. The timeline shifts from watch and respond to wait and speculate, and models go hungry for fresh observations. The hard truth is it's not about bad satellites, it's about physics. No light in darkness. Scattered and absorbed light in deep cloud. Conventional imaging can't change the rules it relies on. If sunlight can't help, bring a different kind of light, one that doesn't care about night or weather. Enter radar. How do you make a sharp image with no sunlight and a sky full of storms? You bring your own light and listen to the echo. That's the simple idea behind radar satellites. Instead of waiting for the sun, a satellite sends out short pulses of microwaves, then times the tiny fraction that bounces back. Clouds don't block these wavelengths the way they block visible light, and darkness makes no difference. The satellite carries both the flashlight and the ears, so it can see when everything else stalls. But radar isn't a photograph. It doesn't record colors or shadows the way your phone does. It's geometry in time. Each echo is a clue: how far away, how the surface tilted, how rough or smooth it is, and how wet it might be. One pulse would look like random speckles. The trick is turning a swarm of messy echoes into a clean, detailed map you can act on. That takes careful timing, phase measurements, and motion. Here's where the wavelengths matter. X-band is short, good for fine detail on buildings and ships. C-band balances detail and coverage, widely used for wide area monitoring. L-band is longer, better at picking up structure in forests and seeing through leaves to branches and trunks. All of them cruise through cloud decks. On the ground, brightness changes with surface roughness, moisture, and viewing angle. Calm water looks dark because it scatters the energy away from the sensor. A metal container yard looks bright because it bounces energy straight back. Wet soil lights up more than dry fields. The result is not color, but a map of interaction. If optical is a flashlight, SAR is a bat. The synthetic aperture part comes from motion. As the satellite flies forward, it hits the same patch on Earth again and again from slightly different positions. By combining those repeated echoes, it acts like a much longer antenna than it actually has. Longer aperture means finer detail. It's like walking past a mural and stitching together dozens of quick glances into one crisp image. Mechanically, each ground point is illuminated over many pulses. The system records not only how strong the return is, but the phase, the exact position in the microwave wave cycle. Tiny shifts in phase between pulses tell the processor how to focus the image along the flight path, sharpening targets that would otherwise blur. Timing locks in distance across the flight path, so you get resolution in both directions. It's math-heavy, but the outcome is a clear, usable scene. Operators choose modes based on the job. Strip Map sweeps out a steady ribbon with uniform resolution, great for corridors like coastlines and rivers. Spotlight dwells on a smaller area longer, stacking more looks for high detail on cities, ports, or landslides. ScanSAR hops between swaths to cover huge areas fast, trading some sharpness for reach. Ideal after a storm when you just need to find the worst flooding. With interferometric SAR, or NSAR, you compare two passes and track phase changes to measure ground motion down to millimeters, revealing subsidence, uplift, or the slow inflation of a volcano. In practice, that means flood maps under hurricane clouds in hours, while water still rises. Oil slicks show up as dark, glassy patches, even under a storm deck. Metal ships pop bright through rain and at night, and their wakes cut thin lines behind them. Urban damage patterns emerge as changes in backscatter from collapsed roofs and shifted walls, guiding teams to where help is most urgent. So SAR turns invisible microwaves into layers you can act on: water extent, deformation, structural change, motion. When optics can't see, echoes still speak. Now that we can see in the dark, the next part is how to put that capability to work, from fast response on the ground to long records that track a changing planet. When light fails, information doesn't have to. Radar satellites keep working through storms and at night, turning microwaves and echoes into maps of water, damage, ships, and shifting ground. They don't wait for a break in the clouds. They create their own path to the surface and feed decisions when timing is tight. So the next time a hurricane makes headlines, pull up the SAR layers from agencies and platforms that publish rapid maps. Watch how responders trace flood lines and scientists spot structural changes hours before skies clear. The invisible world isn't empty. It's full of signals, waiting for the right kind of light.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.